My name's Anthony. I'm presenting work that we did on perception and motion planning to help a mobile manipulator, in our case, the Rule of Garage PR2, interact with moving objects. The title that we used for the paper is a mouthful, so I'm going to switch to our working title that we prefer. Because this gives you a sense of where we were coming from. We've done a lot of work with the PR2, and I bet everyone in this room has seen videos of the PR2 doing amazing things. And then you look down in the corner of the video, and you see that it's sped up 2x, 4x, 8x, or even more. And it takes a little bit of the shine off. And we've noticed that with our experiments too, is that the videos look good, and you see it in person, and when it works, it can be a little disappointing because you're waiting for the robot to do its thing. On top of that, you have the typical research robotics problem of a demonstration being very fragile. It has to be set up just so, speeds and distances measured very carefully. So we said, we want to address both these things, speed and reliability. For speed, we said, look, let's not let the robot determine how fast things happen. Usually in robotics, the action happens when the robot gets there. We said, no, the experiment is going to set the pace, and if the robot's late, that counts as a failure on our part. So we really want to force the issue of pacing. So speed, moving object, reliability, but we are engineers, we wanted to keep it practical for ourselves. So we thought, conveyor belt. We're going to do assembly line work with the PR2. So we bought a conveyor belt. We went to the dollar store, we bought a bunch of objects. We didn't manufacture things that would be easy to see or to manipulate. We said, look, humans have no problems with these things, we should be able to do it. Then we went online and looked for general purpose robots working on conveyor belts, and we found some videos, and it looked like the belts were moving at around 6 centimeters per second, and it looked pretty slow. So we said, we got to double that. We need to hit 12 centimeters per second, and we will say mission accomplished. I was responsible for perception on this. My colleague Ben Cohen is here, he's the planning guy. So the man with the plan is there, and you can ask him all of your planning questions. The connect on top of the PR2's head was my responsibility. So this is what the robot sees. This is our belt, as seen from the robot, one of our objects. Kind of an interesting object because it has a handle. This is a little plastic spritzer bottle you might water your plants with. The tricky part is that the gap between the handle and the bottle is very narrow compared to the size of the PR2's fingers, which you can see in this picture. Those are some big, chunky fingers, and they don't really like to go into small places. So we actually have about a centimeter of clearance if we want to be able to pick up this kind of object. You can also see from this picture that this is a working lab, and there's wires on the floor, there's office furniture, and there's going to be general clutter. And in fact, this is not a clean lab. This is a lab full of graduate students, and they're going to bump into the robot. They're going to bump into the conveyor belt. They're going to put items on the conveyor belt to confuse the robot because that's funny. We needed to be robust to all of them, right? We didn't want to say, lock down the lab, we're running an experiment. We want to be running experiments continuously. So let's see what perception has to work with. It's a Kinect, an RGB sensor, so we get depth per pixel. And if you've done vision for a long time, this kind of image is awesome because immediately the scene starts to make sense without you having to do much. The floor is easily distinguishable from other things. When you have objects of similar texture and color that are one in front of the other, you can still see the edge. We can segment the image based on depth discontinuities, then run connected components, reject obvious things we don't care about, like the floor or things that are far away. And now the big pieces in the workplace become readily apparent. So one of the minor responsibilities of the perception system was to find the conveyor belt. We wanted to have this so that PR2 could drive up to the belt and start its work day. So the way we go about doing this is we run this continuously throughout operation. Perception looks at an image like this, and it says, are any of these segments, do any of them contain a preponderance of points that are well described by the equation of a plane parallel to the ground? Pretty straightforward. We find such a segment, and we consider the inliers that are well described by the plane equation, and that's going to give us the height of the belt. Our belt is very adjustable, not calibrated, but adjustable. So perception can help with that. We will consider the eigenvectors of the covariance matrix of those points on the plane, giving us an orientation for the belt, and the points themselves giving us the side edges, where we're going to want to position the robot so that it can maximize its range of vertices. Once we know where the belt is, it makes it easier to find objects. We're going to deal with multiple objects on the belt simultaneously, but let's just consider one object at a time. So we've now identified a cluster of points that belong to notionally one object. We recorded reference information for the things that we wanted to pick up. We wanted to do this really quickly and really cheaply. So we used the RoboEarth software, which uses printed QR codes to localize the Kinect as you move it around an object. And it's just dumping all these point clouds into one coordinate. This is really noisy, and this is a very advantageous angle I took a screenshot from. There's actually lots of artifacts and weird errors. We thought this is great, because this is another problem for perception to deal with. We don't want to require a laborious process of getting a new object into the database. This is just, you take the same sensor the robot's using and effectively spin the object in front of it, and you're done. It takes 5 minutes. So this is one of our noisy models to it. And what we want to do is we want to recognize the 3D geometry of this thing, and we want to find it on the surface of the belt. So here's that image again. So we're going to consider 2D transformations, because all our objects are going to be on the belt, which is flat, and they're going to be upright, because a lot of our objects would roll off the belt if they had tipped over, or there's one bit to manipulate. So we have translation and one axis of rotation. Another curious aspect to take note of from this vantage point is that we are not looking straight down on anything. We're looking down the belt towards the objects that are coming towards us. So now if you imagine a box coming towards you, okay, you don't see the back sides of that box. So if you go by only what you see, then your estimate of where the centroid of that box is going to be biased towards you every time. Our objects aren't huge, but they're big enough that that bias, on average, was shifting our estimate of the centroid by about 3 centimeters, which completely blows our tolerance. We had a centimeter or less to work with to pick up some of those objects. What that means is that we couldn't do the usual thing of finding the translation component of the pose estimation by just saying the centroid of the observation is the origin and now rotate it up. We need to robustly handle partial observations. As a simple example of how we did this is a 2D case. This is my 2D model of an object. So we take such a thing and construct a cost function, which is just a distance transform of that object. Every pixel here is colored to encode how far away it is from the surface of the object. Now, given an observation, given a partial observation, at an unknown pose, you can imagine just drawing it onto this figure and see what color all the pixels of your drawing would pick up from below. We sum over the entire observed shape, and that gives us a cost. And now we're going to optimize this. This is going to be a nonlinear optimization. We use a very simple strategy due to Powell's dogleg method. So what Powell's dogleg method does is it does a linear optimization along each degree of freedom independently. And then, before the end of the iteration, it considers a linear combination of those just computed minimum and does another linear optimization along that. So the easiest example is if you only had translation, go along x, go along y, you've got a diagonal line, go along the diagonal. So we're just going to evaluate the cost function over and over again through that method until we converge in some local value. And you can see that when we overlay that over our model, we don't see a big bias. You know, that observation of exactly half of the shape, we tend to shift our origin fairly dramatically. But we don't have to worry about that because the cost function effectively captures it. So what perception was ultimately responsible for in this project was to say, I'm going to segment point clouds on top of the belt. I'm going to characterize them by color statistics of the observed points, the overall size of the shape, the bounding classes, to identify a number of possible models that could have generated this observation. Then I'm going to take those possible models and the tens of thousands of points from the observation and run a nonlinear optimization on each of those. I coded this all up in a functional programming language Haskell, and then we run this on a desktop computer that happened to be in the room. It had a very modest graphics card that was released quite a few years ago, and the marketing material describes it as adequate for a light office work. But it was sufficient to do all of our recognition and pose estimation in 20 hertz. So this was not a limiting factor for us in this. Now, once we can classify, identify objects, and get a pose estimate for them, we can start talking about coordinate frames. The PR2's proprioception is fantastic. It knows where its hand is in its coordinate frame very well. Now we can think about where its hand is in the coordinate frame of the object. And if we recover a transformation that tells us where that object is, we can transform PR2's gripper pose into the object's coordinate frame. So we see the object, and now we're going to start training the PR2 how to pick things up. This is what we call the pre-grasp pose. So we have the PR2 in the management mode, where we can drive it and pose it. We put its hand somewhere before the real action is going to start. So the PR2 is going to have a computer trajectory to get its hand into position. This then leads to the grasp pose. Now, when the gripper moves along the line from pre-grasp to grasp pose, it is also closing its gripper as fast as the PR2 is capable of doing, which is very slow. We're doing it as fast as we can. It is now coming into collision with the object. So some crazy things start to happen at this point, and this collision is open loop. So we're picking these points carefully to try to get as stable a swooping action as we can. The third pose lifts the object off of the belt. And what the software sees is just what you'd expect. This is the ARVIS visualization. You see the object, two gripper poses. It's just what we want. So now how do we get the arms into position? We use the SBPL planning library from Max the Fishhouse Lab. And this is Ben's area of expertise, and he will talk to you more about this, I'm sure. We can give the planner several times at which it could pick up an object, and it plans routes all of those goals simultaneously. Once we picked up an object, we attach collision geometry, and then move it to the side, and we're going to drop it off in a basket. The planner is capable of very complicated things. We're using a trajectory splitter by Ken Anderson that gives us an estimate of how long those trajectories are going to take to execute. We broke our trajectories down into segments using these pre-grasped and grasped poses. So we could tolerate a few milliseconds of error, and that really helped us by having these shorter segments. You can also see that the planner was given an upright constraint so that the robot would not flip things over as it manipulated. This is all happening at 1x too. That's the planning time after we picked up the basket. So this was where we were really trying to strain the motion planner. But back to our main system. We were able to run over 2,000 pickup operations. We were able to run the software for about 8 hours a day. This let us conduct science on this system. We could say, let's do 100 consecutive pickups and look at the statistics. And that's how we tune it. We have a system response time of around 400 milliseconds, and we were able to achieve the maximum speed of the belt. So this just turns the knob all the way to the side. And that turned out to be 33 centimeters per second. Blew away our goals. That response time of 400 milliseconds is very conservative. We observe an object 3 times before perception says, I'm sure of what it is, I'm sure of how fast it's moving and where it's going to be. If we drop it on that requirement for a more benign environment, we can have the robot start moving in about a quarter of a second from when the object first becomes visible. All of the time here is spent with PR2 moving. PR2's motion to go grab an object takes 4.5 seconds. Planning is taking about 180 milliseconds and planning for 2 arms. One arm can't make the grab, the other one tries. I'm going to let the video finish, and I'd be happy to take any questions.
Thank you very much. Okay, we have time for some questions here from the back.
I just wanted to ask, the pre-grasp configurations, can I accept any configuration, or you have a space limit where you can, because I see the examples, for example, the shoe. What if the pre-grasp is on the back?
So another limitation that we have is the PR2's reachable workspace. That they cannot reach around the backs. Yeah. So absolutely, there are configurations of those objects that the PR2 can't work with. So the shoe, for example, pretty much has a little bit more than 180 degrees that it can be rotated for the PR2 to be able to get its hand. From the back or the front. Yeah.
Okay, further question from